everyone, and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker has developed to help scientists around the world look into things and discover. So today's topic is materials research diffraction, specifically on the D6 phaser. The D6 phaser is a new benchtop XRD that takes it well beyond standard powder diffraction. Now, it's built on the idea that the system is very accessible, it's very powerful, and versatile. So in addition to materials research topics, we're going to be talking about that versatility. Now, to see the thing in action, let's head on over and actually see the instrument. Good morning, Jonathan.
Good morning, John. Thanks for having me on.
Yeah, so thanks for joining us again.
Of course, good to be here.
And thank you also for joining us. So we have the D6 phaser. This is part 3 of our 3-part series talking about those 3 facets, the accessibility of the instrument, the power of the instrument, and the versatility. And really it all comes to a culmination in materials research.
That's right. Yeah, so with this instrument, we've really taken a lot of the technology that we've enjoyed on our floor standing instruments and brought it over to the benchtop.
So now kind of going through some of those facets, that accessibility, let's start with. For materials research, how does that play into it? Why would we need a machine that maybe is a little more accessible?
Well, for number one, the floor standing instruments are a much higher price point than something like this would be. If you're a laboratory that's doing a lot of powder diffraction and you need to be able to do some materials research measurements like residual stress, texture, even some thin film work like grazing, incidence, diffraction, or X-ray reflectometry, this is the perfect instrument for you.
All right, and there are some pieces I know that people really do enjoy, especially in the accessibility side for materials research, and that is the window.
That's right. Yeah, It's nice to be able to see what's going on, especially when you have all these drives moving and things like that, right?
Yep, and then the other one is that touch screen.
So the touch screen I could see being utilized so much at user facilities and things like that. You have expert users that can go in and program these buttons, right, for different types of experiments. But then a user can easily come up to it that maybe doesn't know so much about X-ray diffraction. They just want the data, and they can go up to the instrument, hit a button, get their data, and be happy. And
okay.
Yeah.
So then, this term materials research, let's just talk a little bit about that. Sure. Because for some people it's a little unfamiliar. So when we say materials research in terms of X-ray diffraction, what are we talking about?
So a lot of bulk material work and thin films.
Okay.
So in the case of this instrument, if you're a polycrystalline thin film grower on some substrate, maybe you want to know what the phase structure of the film is, or what the thickness, density, and roughness of the film is. So this instrument can tell you that information. On the like, let's say if you're a metallurgist and you're making, you're sintering these metallic components, these bulk metallic components, and you want to know what the residual stress state is at the surface, this instrument will tell you that. It'll also tell you if you're, a metal roller, right? It'll tell you what the texture is, and you can go in and actually see what the crystal orientation distribution function is.
All right,
using this instrument.
Yeah, so in those classic powder techniques, we might be looking at phase identification, but then also going all the way up, we had seen in a previous episode, you could take this through structure solution and doing PDF analysis and things like that. So you can really go far in that classic diffraction approach. Here, we're adding the element to the despacing measurement of geometry.
That's right.
Okay, so in terms of then the instrumental setup, now how is that going to change? What's key to unlocking materials research? So
the key thing here is, again, on the D2 and now the D6, you have those coupled theta-theta drive that move together. To decouple the incident and diffracted angles, we have this omega plus Z stage. We call it the universal stage.
Okay.
So go ahead and hit the button to open the door, and we can show you a little bit more about the instrument.
All right, so here we go. Now, in terms of power, we had talked about power too. What kind of power do you need for doing materials research?
So we sell this in kind of 2 models, right? We have the 600 watt and the 1200 watt.
Yes.
In front of us is the 1200, but the 600 will do just fine for any materials research applications. It's just going to be slightly longer collection times.
All right.
Factor of 2.
So you don't need the 1.2 kilowatts in order to do all the measurements. You just get them a little bit faster.
Yeah. I say I need it, but no, not everybody needs it.
And certainly the other trade-off of that is that if you're looking at one of these instruments and price becomes an issue, you can get other accessories instead of going for the higher power.
Exactly.
And also there's a lower power requirement, right?
That's right. Yeah, so it makes it easy to plug it into a standard wall outlet if you go with the 600 watt.
Okay, so 600, that just requires the 110, 120.
Yeah.
Whereas the 1200, that one would require the 200 volts that you'll find standardly in Europe, but here in the States or other places, that'd be a special outlet, still available.
Yeah, exactly.
But, special outlet. So this here, that's the standard stage, or the universal stage.
So we have the universal stage here.
Okay.
This gets you the omega offset, so it'll actually basically tilt the sample like a rocking curve almost, right?
Okay, so that means that this thing is going to tilt this way.
It'll swing back and forth, exactly. So then on top of that, we have the index phi rotation attachment, which is really useful if you want to do texture and things like that.
All right, and then the other part, and that's an accessory piece,
That's
right?
also an accessory, yeah.
Okay, so then also that universal stage, that's going to give you the height adjustment to accommodate different sample heights.
Exactly, different sample heights, and it's critical when you want to align the X-ray beam to a thin film.
All right, so now you had mentioned that we can put on this phi attachment, and this will add the ability to set it at specific rotation angles.
Yep, that's right.
But you can also do powder, right?
Yeah, exactly. So you can do continuous rotation to basically get the best crystallite sampling statistics.
All right. So one thing that we've kind of said before is that this combo, this stage plus that phi gives you a truly universal solution.
That's right.
Right.
Yep.
Okay. So you can though put other attachments on here, right?
You can, and we have a couple right here. So if you're only really doing thin films, then this is the stage for you. So this is the vacuum attachment. Basically, it's just 4 screws. You can see they're retention screws.
Okay, so
they don't fall
That's
out.
great.
That's right. Yeah, it makes it really easy. The phi attachment comes off with 4 screws, and the architecture of the system is a CAN bus mechanism, right? So it's like what we use in cars today.
Yeah.
It's decentralized, so all of the electronics are integrated into the stage motors and things like that. So it's one cable that you literally just disengage it in DaVinci in the software, unplug it, put the new one on, you're done.
All right, and that's really nice if you especially have those 5x5s, 10x10s. You just put it on there. You don't have to worry about tape, anything like that.
And the standard stage is the spring stage that comes with this. So you could put a powder on here, and you could put any bulk samples on here. And you, keep in mind you have that motorized Zeta line too.
All right,
as well.
And all of that is also compatible with the mass.
That's right. So on here we have the motorized anti-scatter shield. And yeah, all of it's compatible with that. You can see we have the shield retracted right now because we're not going to need it today. But if you were doing a powder measurement and you wanted dynamic beam optimization, that makes it really nice, especially if you're doing low angle.
All right, so I'm guessing that a lot of people out there are wondering, this is quite a bit of kit now that we've put into this. Is that something that we can change? Can we take it off and then do the other stages like that we had looked at before?
Absolutely, yeah. So, I mean, you can take the universal stage off the central hub. It's very easy to do. Again, it's just one cable that plugs into the instrument.
Okay.
And then we have the 12-position auto changer if you're doing a lot of powders. We have the capillary stage, right? That's another big one. The powder rotation stage. And then there's also a heating stage, right?
Yep. And then the standard stage too, where you can measure that in the flat plate transmission.
That's right, and transmission,
So you can still swap things around. It doesn't lock you in, anything like that.
Yeah.
So now some of the other configuration parts, we talked about the power, but what about the tubes?
So the tubes are the same tubes that we use in our floor standing instruments.
Okay.
And we offer a variety of wavelengths that you can use here, and they're user swappable.
Okay. And so it is really easy. This system here is the accessibility from the top. It makes it really, really simple that you can just get in there, take those tubes out. And what radiations can we change between?
So we can do chrome, cobalt, copper, molybdenum, and maybe a few others.
Okay. So, and do you need then to have a different optics or different detectors for those radiations?
No, so that's one of the nice things about the design of the system is with slit optics, it's pretty much wavelength agnostic.
Okay. So whatever your needs, if you're looking at something that requires a different radiation system, will get you covered. Then the next part here is going to be the optics.
That's right, yeah.
Right, and so what do we have?
So we have essentially a motorized slit.
Okay.
That could be changed variably during the measurement if you're doing something like dynamic beam. And then there's also an axial Solar collimator inside of there to keep the axial divergence nice and tight. And then there's also another position for a fixed slit or a filter at that primary side.
And if you do put a slit there, we do have special slits that have a little adjustable screw so that you can center that right on the beam. And speaking of that, how is it that we actually create a parallel beam for some of these techniques like GID and XRR?
That's a great question. For the most part, by using a small slit, we're able to achieve a full width half max on like like a silicon standard, very similar to that of a mirror. If we use a very small slit and approach the actually the anode size on the actual tube, so by matching those, you're basically eliminating the diverging part of the beam.
So you would use a small slit, and then if you wanted to, you could add that extra adjustable slit just to clean things up a little bit, get a little bit more refinement.
Exactly.
So then on the detector side of things, we already talked about the middle. On the detector side, what detectors would you recommend for materials research applications?
So honestly, any of the 3 0D, 1D detectors that we have would be suitable. Obviously, the XET is going to get you the best energy resolution, but if you're doing XRR, you're going to be running in high dynamic range mode anyway. So the SSD 160 would be fine. You're just going to you have a little bit less strips for powder diffraction measurements, which isn't critical for XRR, right? You're using 1 strip anyway, usually. And then the Lynx i2 would do just fine as well.
Okay, and then, so all of those can do those higher dynamic range, but when we talk about the XET, what does that bring into it?
Brings in the high energy resolution, about 380 EV energy window for basically blocking out X-rays that we don't care about.
All right, so that'll even get rid of K beta.
That's right. So it actually gives you a nice speed boost too, because you don't need a metal filter.
All right. Now sitting in front of it, we have a special position. We call it the detector optic shaft, huh?
That's right. Yes. So we have that, and then a bunch of components that slide in and out, depending on what types of measurements and experiments you're doing. Right now, we have this set up for XRR. So you can see there's this telescopic slit shaft here, and right on the end of it, I have a basically a cleanup slit for XRR, so we get nice low background as we perform our measurement.
All right, and what are the other options that we can put in there?
We have with me today an equatorial Solar collimator. So that's going to ensure that you get a nice parallel beam coming into the detector in the equatorial direction. And that would be used for any 0D measurements like grazing incidence diffraction. You'll see in texture today we're going to be doing 0D phi scans, so that's useful for that. It can be used in residual stress too if you want to eliminate any peak broadening.
And you do have different sizes of these for balancing resolution versus intensity.
That's right. So we're going for all intensity today with the 0.4. We also have a 0.2 degree and I believe a 0.1, but I would have to double check that. And this is just a 2.5 degree axial solar that you would use for 1D measurements like powder diffraction, eliminating those kind of low angle tails on the peaks at low angles. Because again, you have like the superimposition of the Debye rings, right?
Yeah, so to give you guys an idea how these work, maybe if you grab that one. So if we hold this up here and I tilt it up and down, sometimes I think you can see through it, but the fins are this way, horizontal. The fins here, on the other hand, those are vertical.
Yep, see that if I go with left and right, you can see through, now you can't.
So that gives you a better resolution for the powder diffraction, things like that. This, on the other hand, this gives you the insensitivity to any height issues, things like that.
Exactly.
Okay. Or broadening of the signal across the sample surface.
Yep, that's right.
All right, so those are all the components. So I guess we can see now how it all comes together.
That's right.
You've prepared a few measurements for us?
We have, yes.
Okay.
So why don't you go ahead and shut the door. And this is going to just turn the generator on automatically for us. And then I programmed a couple of buttons in for you today.
Awesome.
So you can see I have XRR on ITO predefined as a measurement in the software and on the touchscreen. So we're looking at indium tin oxide on glass today. And I'm thinking it's around 30 nanometers or so, but XRR will tell us the answer. So why don't you go ahead and hit that button.
All right, so I just pressed the little play button.
That's it. And so while this is now ramping up, we can take a look at the computer screen. This measurement I have defined in our wizard for planning. We commonly use that to plan our measurements. And so I have 3 different segments here. Instead of using a copper absorber to keep the detector linear at those, like direct beam conditions. I'm basically just ramping the power of the tube up as the measurement proceeds in different in these segments. So as you go deeper and deeper into the sample, you lose more and more X-rays, right?
Yep.
So you can see I start off at pretty much standby current and voltage, and then I ramp up. And so this basically eliminates the need for any copper absorbers or things like that to get nice linear measurements.
All right, so that ability to change the power dynamically with the wizard plus the dynamic range of the detector is suitable for this very, very high dynamic range measurement.
That's right. Yeah,
All right.
because we're looking at orders of magnitude and intensity, right? So,
all right, and we see that the machine has actually moved all the way down to that XRR geometry.
Yep.
And then here in the scan, we see that the beam is kind of, as it goes up, it's starting to fill the whole sample, the plateaus, because it's reflecting the whole sample surface, and now
we get this critical edge right here, which basically is determined by the density of the top surface of the sample.
All right. So, and then we start to see these fringes.
That's right. So you can see that's our first segment. Now it's going to go ahead, ramp the voltage and current up for the second segment. So here we're ramping up to 600 watts now. And I can go ahead and overlay the previous measurement. While we're waiting on this, we can go ahead and look at some example data that I've collected. Same sample, same instrument. You can see I was roughly about 5 nanometers off on my thickness estimation.
Yeah, so now this method that you're using, this is something we call FFT, right?
That's right, yes. So
that's
Fourier transform.
Fast Fourier transform.
Yep, exactly. So this is going to get us a nice, quick, and easy thickness measurement by looking at the distance between the fringes, and it's just a click of a button in our software.
And one thing that's kind of interesting about this particular sample is that we know that there are indications, and you can see that in the doubling, that there's 2 layers. And if I look there in the FFT, we can even see that little bump there.
There's a little guy there. So there could be something else that we don't know about this sample.
So it may be, we actually think that the sample is two areas of the sample.
Yeah, so this is XRR in a nutshell. We have another video on YouTube featuring me that goes over kind of more of the software part and fitting and things like that. But this is just kind of a good example of how you can collect and analyze data on this instrument. And you can see that all this data is collected piecewise here. And we can go ahead and just hit merge scans, and it'll merge.
And it'll bring them all together, and there you go.
It automatically scales them. It's
hit the FFT, and you're good to go.
Yeah, it's nice.
Okay. So, so that was X-ray reflectometry. So now the next technique that we might do on a film is what?
We're going to keep the same sample on there, because we know it's polycrystalline. So now we're going to look for phase information. And in that case, we're going to do grazing incidence diffraction, because there's glass underneath this, so I want to avoid the glass, otherwise I'm going to get this giant amorphous signal. So what we're going to do is keep the incident angle fixed using that omega stage.
All right.
God bless.
Thank you.
So we're going to just cancel this experiment now, because I think you get the idea, right? So we'll just hit stop up there. It's going to go ahead and stop. It's going to go ahead and park.
So it moves the drives to just a convenient location for exchanging.
And then what we'll do is we'll have you open that door after the generator settles down. And then I'll go ahead and swap out the telescopic slit shaft with that equatorial solar collimator. And we're ready to roll for the next experiment, because the sample's already aligned.
All right, great.
All right, we're ready.
All right, so I can press the button here, door. And it always gives you a fun little noise there.
Yeah, that's right. You get the nice ding. That's how you know it's done. It's ready.
And in the background, while we're waiting for the door to open, it's something you can't really hear, I think, on the camera, but there are some little clicks and stuff going on, and that has to do with the safety circuit.
So it's just a couple of set screws on here. And then this pops right out. So I don't know, John, maybe you want to show that to the viewers today. And I'm going to pop out this filter as well.
So that's the telescopic slit shaft. And the reason it's called telescoping is because you can loosen that little nut, and then this can slide further out or in. So if you use the same optic for capillary diffraction, then you go farther out. Then for XRR, we retract it. One optic, multiple things. There we go.
Multi-purpose.
All right, so then back to the inside, and we could see.
So now I'm going to insert the equatorial solar collimator in that same position. And again, same mechanism here.
Yeah, these kinematic mounts really make it easy to exchange things. And I think that's always important for really optimizing a measurement. to not have the hesitation. Because maybe you make a measurement with this 0.4, and then you go, I'd rather have more intensity or more resolution.
Right.
Right.
Yeah.
So now you go down to the 0.2, and it's so simple to do.
Right. Exactly. All right. So we're ready.
So that's it.
That's it.
Just change the one thing.
Just change the one thing.
All right.
You can see it's in there. It's not going anywhere. Yep. Now we're going to do some grazing incidence diffraction.
All right. So now I imagine in the software we're going to have to set up a whole bunch of stuff.
Well, I've already predefined a button for you to click again. I made this really easy for everybody today. Yes.
So if this was a user lab,
Yeah.
You could just make these buttons and tell the users, make sure, take a picture of it. This is what you should have in there, and you'd be good to go.
That's
or
it.
they can check DaVinci.
So when we start the experiment, we'll go in and I'll show you exactly what I did to plan the measurement. So why don't you go over to the page where all the experiments are? Yeah, just scroll to the
over.
right. Yep.
Okay.
And then you'll see I have GID on ITO. Go ahead
All right.
and hit
So we hit the play button there.
And so what it's going to be doing now, if we go over to the software, is not only is it going to be ramping up the generator, but we're also changing the detector settings to high resolution mode. And it's also changing the detector window to match what I had in my wizard settings for the experiment.
And in both of these modes, we are using 0D mode.
That's correct.
Right?
Yep.
Okay. And that's not something you had to physically change anything. It just automatically bins them
did it.
differently.
You can see it changed the slit width.
Yep. And all of this is programmed in the wizard again.
That's right. So we can go actually take a look at that now while we're waiting for this to ramp up. And I'll move over to my GID experiment. So you can see in DaVinci here, this is where I go ahead and set my detector settings. So you can see detector opening about the same size as the window on the equatorial solar. And then I'm in high resolution mode because I want the lowest background possible. And then full power because, grazing incidence, you want the most flux you can get off of that sample. You can see I set the slit size here. And then it's very simple to just go into the setup and put your experiment conditions on. You can see it's a 2 theta scan, effectively a detector sweep because we're just keeping the incident angle fixed.
Okay.
And you can see right now how if we go to the instrument for a second, you can see how now that there's an omega offset applied to keep that incident angle fixed.
So that sample, it's all tilted.
Yeah.
And then this is here, and it's slowly moving. And it is kind of a complex measurement in this machine because it's that the arms go up and the sample goes down. That's the fundamental motion, but then it also is tilting the sample.
Yeah, so it has to keep those precisely coupled together to keep that incident angle fixed. So it's pretty cool engineering.
All right. And then,
so yeah, you can just see again if I turn to the software, I can set the angle of incidence here. So from a user point of view, you don't have to think about any of that.
Yeah.
It's just how do you want the experiment to run, and you hit go, and even make a button if you want to run multiple measurements. Yeah,
it's kind of one of those, it's a very nice balance.
Yeah.
So it's not going to be too intrusive. It's not going to be forcing you to, click the same thing over and over again. And then once you've done it a few times, you're like, again. But at the same time, it's really guides you through that setup.
Yeah.
All right, so how's the measurement looking?
Let's take a look. Oh, there you go. You can see we have some peaks. I'm just going to get out a log scale here. There you go.
Yeah.
So again, this is a really fast grazing incidence diffraction experiment. If you want better signal to noise, I would collect probably longer than 2 minutes.
Yes. Yep.
But we have some example data that we can look at that I've collected on this same sample.
Okay.
In 2 different modes. So you can see on the top here, if we turn to the computer, that I have our grazing incidence measurement where you see all these crystalline peaks come out from that film, that 25 nanometer film on the surface. If we remove that, and just look at what a coupled scan would look like, you'd see it's this amorphous component. You don't really see any crystalline peaks.
So you get some indication that there's some peaks there. But it's mostly just the glass.
Right, exactly. And so then we can go ahead and do a little phase ID, and you can see this is indium tin oxide. Yeah.
Wow. Yeah. Okay, so that's simple. And
that's it.
And there you go. And like we had measured before, it's actually a 25 nanometer film.
That we're getting information from 25 nanometers. It's unbelievable.
Yeah, and by keeping that incident angle low, we're able to get additional information from the top. So GID, XRR for films, good to go.
Yep.
And by the way, if everybody looks here now at the geometry, you can really see how that's different, right? That sample is still at the 0.5 degree angle of incidence, and meanwhile that tube
now it's
was
coming
way
back
up here.
down because it's done.
There we go. Yep. And then it's ready for the next.
Yeah, exactly.
Perfect
it's ready,
timing
waiting for you. Yep.
Okay.
All right, so now what we're going to do is run a texture measurement on an aluminum sample.
Okay.
And I've also made a button for this. We're going to keep the same equatorial solder in there because we're going to be doing a 0D scan. And as we're tilting this, it'll help keep that peak broadening at a minimum.
Okay.
So what we're going to have you do now is go and open the door.
Okay, so I just press door?
Yep, that's it. And then do you want to swap the sample?
Ooh, sure.
I know, this is a big responsibility.
I don't want to break something. So now the sample itself, this is actually a soda can.
Yes,
right?
That's right.
Okay.
So anybody can perform that at home if you want to.
Here we go.
Got that. Thank you, sir.
And then as I put the sample in, what's nice is that there are some little like spring-loaded balls in there that help to make sure that sample is nice, tight in there. It's
you know what actually would be
out.
really nice to show with the top-down camera is if we show them kind of the metallurgical mounts. I don't know if they, if they can see. There's like little cutouts in there. If you have like epoxy mounts, if you're a metallurgical lab. Makes it really easy to mount those types of samples as well.
Oh man, I remember like years and years of just like mount those, grind, polish, grind, polish, right? And yeah, I mean those fit perfectly in there. And the other nice thing is here you can see those magnets. So if you do have any of our metal holders, it helps to hold it steadfast.
Yep, and then you can also secure it with those screws on the side too.
Yep. So there we go.
Beautiful.
Nice, confident feeling in there. And what else do we have to do?
That's it.
Really?
We're ready to go.
Okay. That's easy. Close the door.
Close the door, you can see the generator will pop back on, and then you can go ahead and scroll to the page where the texture experiment is and just hit go. So texture on aluminum.
Okay.
So we hit that, it'll automatically set the current and voltage.
Did we have to disable anything?
It's all set. We're all good.
We're ready to go. Here we go. So we hit the play button, and then it's gonna go. Now, texture, oftentimes, like I've seen it done though where you side tilt, right?
That's right. So this is going to be within the diffraction plane that we're tilting the sample.
Okay, so this is the ISO inclination
That's
method.
correct, yeah.
All right. So instead of side tilt, we tilt towards the sample or away.
Like a rocking curve.
Yep, and that means that since we're tilting towards the tube or away from the tube, we're going to want to look for reflections that are a little bit higher.
Yeah.
Right. All right.
But you know, it's redundant, and you get the same information. So you'll see when coupled with our analysis software that you can basically get the entire orientation distribution function. So it's
then while this is starting to go, we do have a wizard to help people walk through this too, right?
If we turn over to the computer, I can show you exactly how I plan this experiment. So if we go to my texture wizard, you can see in this case I just did 2 reflections for the sake of speed here. But you can add as many as you want, and then you can basically see how long do you want to collect for. We're doing continuous phi scans. I set the 2 theta for the crystallographic reflection. We can add in background, which is good. If we want to do background subtraction, it'll automatically apply that. On this side, we basically determine how big our steps do we want to make, depending on how sharp the texture is, you know, knowing with some idea going in. And then we set our Bragg limit here to basically determine the coverage that I'm getting within those physical limitations of being a reflection mode measurement. So I don't want the source to go below the plane of the surface plane of the sample. And then, of course, the psi range is then set automatically based on that.
All right.
So it's actually very easy to set up.
Yeah, and you can see that you actually do get pretty good coverage.
Yeah. With these higher order, if I go even to this angle, you see we get even more coverage.
Yes.
So the higher angles, the more coverage you're going to get.
Yep. So now if we look back at the machine, you can see how this measurement is progressing. So it started flat, and then as it's going on, it's tilting it up and up and up, and then it rotates phi at each of those in order to get the data.
Yep.
So pretty straightforward measurement.
Yeah, that's right. And you can see, like, this is the fastest texture experiment ever, and we're getting like these nice peaks.
Yeah.
Right.
Yep. So each of these is a different phi. That's a different circle on that pole figure.
Yep, exactly.
Okay. So now I think you have some results, right?
We do have
that we
results.
Can take a look at.
If we turn over to the computer here, this is again same sample, same instrument, collected a little bit longer data.
Okay.
You know, with multiple pole figures here. So you can see how the coverage increases as we go to higher angle, and we can use all of this information to then go in and calculate an ODF and even recalculated pole figures to fill in the range that we didn't have. Right?
So one thing that's really important for this analysis is that we actually use what's called the component method, right?
Exactly. Good point.
Yeah.
So that's basically, it's based on modeling, and we use elliptical broadening in this case to calculate the ODF.
Yeah, so instead of spherical harmonics, which is that method where it just uses different mathematical functions, here we're fundamentally fitting the data using different texture components. The benefit is that it gives you a direct correlation back to the material.
Yeah,
right? It says,
exactly.
oh, I think this many grains are pointing in this direction with this amount of variability.
Yeah, exactly.
Things like that. Okay, and like you said, the reconstructed pole figures there, that fills everything in.
Yeah, exactly.
Edge to edge.
So you can see kind of where we have, a higher probability of hitting a crystallite.
Yeah.
And then if we go kind of like a classic inverse pole figure view here, you can see in the rolling direction we have 111 texture, and the transverse 101, and then normal 101 as well.
Yep. And for this type of measurement for cans, it's really important you have the right texture. Otherwise, you run into issues like earring when it's pushing the cans out. All right. So that measurement, pretty straightforward on this instrument. So, and you can even see here now it's at the higher angle.
Yeah.
So even more extreme looking.
Yeah, that's right. Oh, and what's really cool about this is I'm using fixed sample illumination.
Okay.
So we're actually getting like reasonable peaks here, even though we're like, look at how fast it's spinning the sample, and we're getting like reasonable information because we're illuminating the entire sample.
Great.
With X-rays, so we're getting a high flux. But that's texture in a nutshell on the D6. Very easy to set up a measurement. Again, if you're doing multiple measurements, you can hit a button. It's very easy.
All right, and then we'll have the next one now, which is the last one, residual stress.
That's right.
So I know that we're a little bit over our 30 minutes so far, but we're just going to keep on going. If you do have any questions, though, that are popping in your mind, you can go ahead and type those on the right side of the screen. We'll get to those at the end. Otherwise, you can also always write them in to our email address, live.events@bruker.com, and we will answer those later. So how do we set up our what do we got for residual stress? What's the sample?
Residual stress, we have molybdenum film there that I've kind of, and this is actually pretty nice too. If you want to mount bulk samples, we have these well holders, and you can just use a little piece of clay and press it in, so the surface is nice and flat.
All right, so there's a piece of glass with some moly on it.
Yep.
And we're going to do some stress.
So you can see our texture measurement's actually done, so it's going to go ahead and go back to park for us.
Okay.
And then we can go ahead and swap the sample.
All right.
And what we're actually going to do is now change out, because we're going from 0 to 1D, we'll swap that equatorial solar out with an axial solar.
All right. So in terms of the measurement, texture, what we're doing is we're looking at the same D spacing, but we're seeing what's the distribution in terms of angular space. With this one, we're going to be looking at the change of the D spacing as a function of orientation.
Yep.
Okay. So are we ready to
We're ready. I'll hit the door open button for you.
All right.
And then let me get my tool and the axial solar that we're going to need to swap out. All right, so
look at that convenient little shelf.
Yeah, I know, right? That's really nice. I love to have that thing.
All right, sample is loaded.
In, and then we'll just get a shot of me swapping this out. Unscrew that a little bit more. There we go. And then this axial solar just pops right in.
All right.
And so when I look at this, I always think the detector looks a little bit naked now, because it doesn't have any of those bigger components on there. Yeah. All right, so I think we're ready to go. I'm just going to go ahead and shut the door. The generator's going to pop on, and of course I made a button for stress.
Here we go.
It's going to be that one. Yeah.
All right.
So I'll let you do the honors.
So I just press the button?
Press the button. Go for it. Stress on Molly.
All right. So residual stress, the coating, typically it's residual because it's stress that remains after the load has been released. For coatings, this typically comes from the deposition condition. So if you have the substrate, for example, is heated up, film is applied at that high temperature. When it cools, there can be a differential in the thermal contraction.
Right.
And that leads to, if you have a compressive stress or a tensile.
So essentially, it's a bit residual strain.
Yeah.
Yeah.
Yep. And in the case of films, if you have that tensile, that means that you get a little bit of a scratch, something like that, peels off.
Yeah, exactly.
So compressive is the way to go for these films. Now, I'm guessing that you've set up another wizard?
I'd be happy to share that with you.
All right, great.
We go ahead and switch to the computer. So moving over from texture, you can see, again, I already set everything up in DaVinci, very similar to what I had for texture. In this case, the detector is fully open, and now I'm just doing, you can see ISO inclination here, offset coupled 2 theta. So it's a continuous scan from 125 to 140 degrees.
Okay.
Pretty large increment because these are typically strained materials with very broad peaks.
Yep.
And collection time 0.2 seconds. So you can see this is a 2-minute, a little bit over 2-minute measurement. And I'm just iterating over different, call it sine squared psi positions. So this is really nice. You can have equal steps in sine squared psi in our software, or you can do regular psi, whatever makes you happy.
Okay.
And then with I'm not doing any rotations here. I'm just doing a simple normal and shear. So if you didn't have the rotation stage, this is what you'd be doing. The rotation attachment on here. But you can also rotate the sample and get the full tensor if you have the rotation attachment.
All right. So in X-ray diffraction, what we want to do is we're going to measure the lattice parameter that's pointing out of the sample, and then we're going to measure it. We want to measure it in the plane of the sample, but we can't get there directly. So what we do instead is we measure several tilts. And then from those tilts, we can extrapolate the stress itself. So you can see here the geometry that it's using is that sample's tilted, and then it's doing a scan.
Yep.
And it's using a 1D mode this time.
Yes, that's correct.
Okay.
So it's like almost like a powder type of scan, except now what you can, if we kind of overlay this. So if we look at the previous measurement relative to a current measurement, you should see that center peak position shifting around.
All right.
Yeah, so you can see this peak is now to the left a little bit more.
Oh yeah, definitely.
Yeah,
definitely
so I'm guessing now that we're getting closer to the diffraction vector being to the sample normal, I'm guessing this is a compressive stress.
Okay.
So, but we do have some analysis that we've done to kind of show you.
All right, let's take a look.
So
at that.
after completing a measurement, you can go ahead and import it into our Leptos software, where you basically are greeted with a lot of scans that you've performed. And then you can go and select what material it is, what reflection it is. It's going to go ahead and populate the elastic constants. And then you just basically set the angle that you measured at, and it's going to go ahead and perform the fit. And you can see we have a nice linear regression here.
Yep.
And the stress on this is actually pretty high, almost, I would say, greater than a gigapascal.
Wow.
So if you want to see this in more detail, we have an entire YouTube video on residual stress. So check that out.
And the negative sign on that stress would indicate?
Compressive.
Compressive.
That's right.
Okay, so it's in the good direction.
Yeah, it's in the good direction. Yeah, so this is a good sample.
All right. So
that pretty much sums up residual stress.
Yeah. So those are just an example of different methods that we could do. So 4 of them: XRR, GID on the films.
Yep.
And then we did texture, stress. And you could do those on films.
Yep, that's right.
Or you can do it on bulk too. And with that, I think we're going to switch over and we're going to start answering some questions. Now, we do have some questions that came in beforehand. Again, you can always write those questions in to our email address, live.events@bruker.com. But let's get to answering the questions that have come in. So from Notiz, is a PDF license included with a device purchase, and can you give an approximate price range to be able to calculate if purchase is possible regarding relatively low sample numbers? So, unfortunately here on Live from the Lab we don't really talk about price. I would say it's in that benchtop category of pricing. So very affordable. So just go ahead and reach out to our sales force. If you go to the website, Bruker.com, right there, that can give you some links to contacting us. In terms of the PDF license, So what does that mean? Powder diffraction file, right?
That's right.
So that's a really, really nice database that's edited, it's editorialized, I should say, by the ICDDD. And they go through, make sure all the patterns are good, they rate them all, very comprehensive editing. That one does cost an additional amount. And they do have licensing and things like that.
Yeah. So I think we have COD in our software by default, but you can easily compile the PDF database.
Yeah, so there is a free one called the COD, the Crystallography Open Database Project, and that one is also available. Yeah. It is more like, say, the Wikipedia.
Right.
So a lot of the files are in there, especially minerals.
Yeah.
So both are options that you can use. All right. Next question is from Tom. Is the universal stage removable so that you can do powder diffraction?
Tom, great question. It is. So you can take it off and pop on a powder stage very easily. Again, it's that one cable CAN bus. You don't have to go to a central motor board and do all this stuff that would require a service call. But at the same time, you can do powder measurements with the universal stage. So let's not discount that. I think if you want to be able to rotate the sample, you just have the phi attachment on there and you're good to go. But also what's really cool with dynamic beam optimization and fixed sample illumination is you get really good crystallite sampling statistics without even having to rotate the sample.
Yeah.
So it depends how what your preferences are.
All right, next question from Farzane. How do we quantify amorphous materials if we can't get any peaks after we run the sample for powder diffraction? Is there a specific software program we need to use to analyze the amorphous material?
For that, I would look at like PDF.
Yes.
So like pair distribution function is what I would go for, the technique for looking at like total scattering and things like that. We have capabilities to analyze that in Topaz, and I think they're with EVA too, right?
Yep. Yeah. Yep, so in EVA, I believe version 7, what you can do is actually do a PDF measurement on the instrument, and then you would bring that in, and you can convert it over into the PDF space.
Yeah.
And then what you can actually do is it gets out the structure from the amorphous. If you have only like one big bump, that gets harder. Typically what we'd be looking something more like, say, cellulose, where you're going to have some structure, but it's very, very long range. And so you kind of a series of bumps that are very broad.
And if all you're looking at is percent crystallinity, you can get that in a powder diffraction scan.
That's right.
Yeah, so.
Yep. All right, next question from Sally. We measure residual stress on steel. Can we switch to a chrome tube?
Yes, absolutely. So again, really easy to pop a tube out, throw another tube in with a different wavelength. Again, the optics are wavelength agnostic, so you don't have to worry about alignment or anything like that. So very easy to do.
Yep, and it's just a few screws to take it out. You don't need to have a service or anything like that. And the water also, when you turn the machine off to change that tube, it's not pressurized.
Yeah.
So you'll get a little dribble of water out, just wipe that up.
Yep.
Otherwise, put it in. It's actually not water, I should say. It's cooling fluid. Right. Yeah. So it has a little ethylene glycol in there. And then you put the new one in, tell the software that you changed your tube, and then you can just run the automatic calibration method. All right, next question from Elena. I am late to the broadcast, so it might have already been answered. What is the sample's max dimensions on the universal stage?
That's a good question. I think that's what, a 30 millimeter holder?
Our standard holders are 51.
Yeah. Okay, so there you go. 51 millimeters on the phi attachment on there. But honestly, you could probably just pop a sample on there that's bigger.
Yep. Yeah, if you had that universal, or the spring stage there, I should say. Yep. So that one, this is roughly about a little bigger than the 51, so probably 55 millimeters in this direction. Probably similar here.
Yeah.
If you did have something bigger, you could probably even set it there.
Yeah, honestly, that's what so again, the clay method works really well. If you use a powder holder, you could just set a sample on top of that, or like some double-sided tape on the back side of a powder holder.
Yep.
And honestly, with this, we could do up to 3-inch wafers, I think.
Yep.
So, yeah.
All right. Next question from Robert. If I have the powder diffraction stage and need to add texture and stress capabilities, can I upgrade my system?
Absolutely. So just kind of like the inverse of, if you want to be able to do powder measurements on here, all you would do is just take the stage that you currently have off the center hub, put the new stage on, and run a reference and verification.
Yep, and those are all, user swappable things.
Yeah.
That's how the system has been designed, accessibility in mind.
Right.
So you can just swap it, ready to go.
It also makes it really easy to upgrade. If you want to start off, with the base instrument, and then maybe you need to add a capability later on.
Yep.
Right?
Yeah, I mean, if anybody's looking at getting one of these, definitely the thing to do, I think, is you invest in, get the power you want on the tube, get your slits.
Get the detector.
If you want the motorized slits, and then get the detector you want.
Yeah.
The other stuff, you can add everything.
Right.
Pretty easily. And then lastly, the question from Christina, how do you make a parallel beam? We touched on this a little bit.
We did a little bit, yeah. So that's going to come from just using a really small slit, approaching that the same dimension as the anode on the source. So that kind of gives you this double aperture, and you're removing all the diverging component at that point. And what we found is, it's comparable to a mirror.
Yeah.
The only difference is you're not getting rid of the white radiation.
Yep. So, and the nice thing, the benefit is then that it's wavelength agnostic, so you can measure with anything, any radiation that you want.
Yep.
Swap it up. All right. With that, we've come to the end of the questions, and thank you for joining us.
Thank you, John. Always good to be here.
Yep. And thanks to everybody out there for joining us today. Until next time, make sure to keep your signal high and your background low.